Hello, all of you, and welcome to the continuation of the nervous system. And we want to look at right now is the action potential. So the first thing we want to think about is, does the entire neuron depolarize all at one time? Is it all happening at once? So you think of this is the soma, and this is the axon, and maybe it's receiving signals, and all of it is going to be able to fire. But that's not really the way it works. So there's an input zone, and the input zone here is all the dendrites. The dendrites are going to receive that information and pass it along the axon off to this conducting zone. We're going to call it the conducting zone there. Remember that the dendrites on their own can do a little bit of their own communication, okay? But this is the most common way that depolarization happens in a motor neuron. So there's a flow of ions, and that flow of ions is going to create current or potential. So that has to do with charge, with negative and positive charges, and what's attracting a flow of these electrons across a membrane. So when that happens, when you have this flow of electrons that's traveling down an axon because of this exchange of ions, it's going to be called an action, because something's happening, an action potential. So to define it, we would say it's the momentary change in the membrane potential, because the membrane in itself has charge. So that charge is going to change. Okay, so it's that momentary change in that membrane potential that's going to serve as a long distance electrical signal. Okay, charge. So how does current flow? Well, think of this in pieces. This is going to be the active site, right? We've received input from the dendrites. And now in this axon hillock, in this part here, there's going to be an active area where that action potential begins. And from then on, it's going to spread down, 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 down. But it's only going to spread if there is a change in potential all the way along the way. And so we call that the adjacent area, and that adjacent area at first will be inactive, and then it will go on to do its thing, which is depolarize. So it's always in this direction. It can't go backwards. It's always in the same direction. And let's go to the steps. This is showing an area where here is the normal resting neuron. Okay, and it's more negative inside, more positive on the outside. And this little piece here is a section of the axon that's depolarized. This is what it would look like. And it's going to influence the area ahead of it. And that charge is going to influence the neighboring charge. It's going to flip, and this is now going to become positive and this negative. This will become positive and that negative because it's affected by the region before it. It can't affect it backwards because those channels have to reset, and it takes a while to reset before they can do it again. So it will only travel down towards, away from the soma. So what channels? And what opens the channels? So the first thing is that they are voltage-gated channels, which means when they get hit by this voltage, when they get hit by charge, they're going to open. This is not how they look like, but this is how we imagine them to be able to teach it, right? We imagine it's a little opening, that something can go through, charge can go through, or it's closed. So they're voltage-gated. This little ball is going to loosen itself. It's going to move away once voltage hits that. So if we made a trace of that action potential, the question is, what would it look like? And this is what it looks like, if you remember from before. So it goes flat a little bit, and up and down and around. But first, let's look at what are the axes here. So this is the membrane potential, and this is over time. So the membrane potential, I said to you, is negative in the beginning. Yeah, it's negative because there's so many negative proteins inside that cell. So it'll be negative. It stays negative until something happens. Okay, and let me just leave it at that for now. and there's going to be a change in the membrane potential. Sodium is going to pour in, and then it's going to come back out, and then potassium is going to pour out, and off it goes. But instead of showing you on this diagram, I want to do it one step at a time. Okay, so let's take these numbers 1 through 9 here and do them one at a time. Here we go. Number 1, the resting membrane potential. Number 1, minus 70. Why? Because the cell is full of negative proteins inside the cell. So number 1, nothing's happening. Number 2, there's a stimulus, depolarizing stimulus. What could that be? It could be someone slapping me. It could be light in my eye. It could be me hearing something. It could be tasting something. It's some sort of stimulus is coming in. Okay? Its stimulus comes in and it changes. That little ball now is going to leave, and sodium is going to be able to come into the cell because there's been a stimulus. So sodium is positive. Sodium is positive. It's going to start letting in positive ions. And what used to be very negative in the cell now becomes a little less negative because of the positive ions. 2, what happens here? The membrane depolarizes to threshold, so more positive, more positive, more positive to a certain extent, at which from then on, it's going to really continue up here and continue its depolarization. So stimulus, channels open, and sodium enters the cell, and sodium enters, and here we are going up, up, up. Rapid sodium entry depolarizes the cell. Now look, we're at minus 10, 0, 10, plus 30 is getting very positive because this sodium is flowing in. Until what happens? The sodium channels are finished. They close. No more sodium will come in at a certain point, at around plus 30 in most neurons. They close, and then potassium channels open. And they actually weren't closed the whole time, but they're very slow to open. So they're sort of slowly starting to do their thing, whereas sodium was much faster. You can see that down below here. Sodium does a big jump and potassium is slowly doing its thing. So we really start to see the more dramatic effects up here when that potassium channels are much more open and potassium is positive. And what happens is that potassium starts to leave the cell. So if we have positive ions leaving the cell, then it's going to become less positive and come back down again in the direction of obtaining more positive, losing more positive ions all over again. Okay, let me say that again because I confused you. Sodium in, very positive. Potassium out, very positive. So this is potassium still moving as we go down number 6. Number 7, the potassium channels remain open and too much of it leaves. Too much of it is leaving. So it becomes actually less negative than to begin with, right? So we call that hyperpolarization, very polarized. But that'll, in 8 here, the voltage-gated potassium channels now are going to close. Less potassium leaks out of the cell. And finally, the cell returns to resting ion permeability and resting membrane potential. So what just happened? Sodium poured in and it made the cell very positive. Potassium poured out and it made the cell become more negative again. That exchange of ions that's occurring all the way along the axon, right, is creating current. So this little action potential is happening. Let me go back to this other diagram that I had for you here. It's happening here and here and then there and then there and then there and then next and then next and then next, and it's going to continue happening all the way along that axon. And flipping this open and closing of channels. And that change of charges is electricity, really. It's current. It's current that's moving along this axon till it gets to the very end of that neuron and then sends a message to another cell and tells that cell, maybe it's contract, maybe it's, move, maybe it's form an image, maybe it's interpret sound. So think of current as the wiring that's sending a signal to another cell. And that's how it happens. It happens with the sodium and the potassium channels changing. The types of gated channels are chemically gated channels, and so it's a neurotransmitter that's going to open the sodium and open the potassium. That tends to happen on that receiving cell, right? The postsynaptic cell. When that neurotransmitter arrives, then it's going to receive that signal. So all these channels function differently. They can be chemically gated. They can be mechanically gated, opened by a stretch or pressure receptor. Think of something like the bladder has stretch receptors. It actually fills, and then finally it sends a message saying, this needs to be voided. So that's something that will send an action potential just because of volume. Mechanically gated. Voltage gated channels, which is what we've been talking about, right? Voltage is going to hit that sodium channel and it's going to open up. There's also thermally gated channels. So when you're very warm, right, at the level of the skin, changes start to happen. Like what? Like you begin to lose water, you become sweaty. If you're very cold, you start to shiver. So these are action potentials that are being generated through something like heat. To detect that, we have thermoreceptors. So 4 types of ions are important to these membranes. Sodium depolarizes the membrane. Potassium repolarizes the membrane. One loses the negative, the other gains the negative. Chlorine channels can hyperpolarize. In the presence of chlorine, it becomes even more negative than the -70. And calcium channels. These calcium channels release synaptic vesicles from the axon terminal and communicate with the next cell. So imagine cell number 1, action potential, action potential, action potential. It arrives to the next cell, releases a neurotransmitter. That neurotransmitter, before it releases a neurotransmitter, those calcium channels have to be open, and that's what's going to make it release the neurotransmitter. Calcium, very important. And that's where we stop. That's the action potential. Very important in the physiology of how the nervous system functions, how motor neurons function. Thanks. Bye.